Good afternoon and good evening. I'm here in Tokyo. It's relatively late, but so I'm going to talk about the possibility of a future space program. Actually, so the title is Prospects of Space Terahertz Intensity Interferometry. And this is still in a very early stage of our development state. And I'm Hiroshi Matsuo at Advanced Technology Center at National Astronomical Observatory of Japan. So the contents. So first I will introduce some of our astronomical observing activities in high angular resolution fine infrared observations. And then introduce Humphrey-Brown and Twist intensity interferometry and imaging technique using the interferometry, followed by the detector technology we are now working on and possible future program. All right. This is one of our recent results from ALMA observing a very distant galaxy at redshift 9.11, which was the most distant spectroscopic identification by oxygen line, ionized oxygen line at 88 micron. It is at 3.4 terahertz. But because it is redshifted, you can observe from ground in some millimeter wave. And it is already resolved, as in this graph. And also, the oxygen emission line is quite strong from quasars. In this case, the quasars at redshift 6.0, and it almost the peak emission is about, say, 10 millijansky in its flux density. And its distribution, when compared to the dust continuum observation and oxygen emission line, the distribution is already different. And the ionized oxygen seems to be distributed widely, and probably it is related to the star forming activity. But because there is a quasar activity, AGN activity at the center, it is of interest to observe closer to the center. Also, you can observe a nearby object with high angular resolution, but actually it is not easy. The situation of the angular scale you can observe is plotted as a function of frequency. In radio frequencies, you can use ALMA, and in near future, NGVLA, and of course, VLBI can observe with a great angular resolution. In optical, you can use large telescopes and interferometer on ground. But in terahertz frequencies or fine infrared wavelengths, the space-borne telescope is limited in its size, and there is no interferometer yet. So there's a large gap of angular resolution in terahertz. So the technology I discussed today is intensity interferometry. Intensity interferometry is known by Humphrey, Brown, and Twist stellar intensity interferometer. And this is the Narrabri stellar intensity interferometer in Australia. It's an optical interferometer with 6.5 meter telescopes with a separation up to about 200 meters. And it observed measured diameter of stars. And this is one of the example observing Sirius. And the correlation, intensity correlation is measured, and it changes as a function of the baseline, the distance between telescopes. So it has proven that the intensity interferometer works, but why intensity correlate? The correlation of intensity is because thermal radiation a fluctuation of thermal radiation is larger than the Poisson fluctuation of photons. And this is the equation given by Bose-Einstein statistics. And there is two terms in its fluctuation using photon occupation number. And if you write in NEP, noise equivalent power, which is the power fluctuation with post-detection bandwidth of 1 Hertz or integration time of 0.5 second, the P is a power, and H nu is energy of photon, and KT is a thermal term, and there is two terms. Actually, this thermal term make a larger fluctuation compared to the Poisson fluctuation of photon. And this thermal term is quite usually quite often used in radio frequency range, like the temperature fluctuation, like with this equation. But this is the source of photon bunching. So what these two terms behaves is plotted in on this view graph as a function. It's NEP versus the frequency in wide frequency range, and in the middle is a terahertz frequency range, and its brightness temperature at 2.5 Kelvin and 250 Kelvin is plotted, and the thermal fluctuation and photon Poisson fluctuation is plotted separately. The thermal fluctuation, when thermal fluctuation dominates, you can observe large photon bunching. So that when the temperature is large enough, say larger than 10 Kelvin or so, then in terahertz frequency, you can observe the photon bunching. So longer wavelengths, the photon bunching is relatively easier to observe. So intensity interferometer works. And optical, the intensity interferometer is relatively low efficiency, unfortunately. So this is the concept of the long baseline intensity interferometry. Well, it is like VLBI, but the input radiation is a stream of photon. So the interferometer make aperture synthesis imaging by using the delay measurement precisely. The delay can be measured either by phase of radiation, or you can use photon bunching to measure the delay time with intensity interferometry, which is our proposal. And the photon signal can be recorded and then later correlated. So the system can be separated. So the accuracy of the delay time can be estimated by using the number of photons coming from stars and AGN. Like at a bright source like 1 Jansky, using 10-meter telescope, you will be able to measure 100 megaphotons per second. It's a large number. Then the estimated delay time accuracy with the integration time of 100 seconds is 0.1 picosecond, which is accurate enough to be used as instead to be used as a phase information. By the way, this equation is used to estimate this delay time. We have made earlier a measurement of intensity correlation using Nobeyama radioheliograph at 17 gigahertz. And the top plot shows the amplitude correlation, which shows fringes. It is usual interferometer fringe. And the bottom shows the intensity correlation. So the intensity correlation do not have fringe, but have just a single peak. And you can understand that this single peak is because of the photon bunching. Photon bunch correlate to make this peak. That is what the intensity interferometer can be understood. So the accuracy of the delay time you can measure can be estimated by this equation. And for this measurement, integration time of 50 milliseconds end up with delay time accuracy of about 5 picoseconds, which we have confirmed actually with actual measurement. So intensity correlation is plotted as a function of projected baseline here, and the delay time is plotted below. So the real time of visibility is actually the square root of intensity correlation, because the visibility, you work with amplitude, right? And the imaginary part of the visibility can be estimated from the delay time. So you have a complex visibility data. So in principle, you can make an aperture synthesis imaging by enough UV sampling with this kind of visibility data. So that's the concept. So we have made some simulation assuming a double star with primarily like a Betelgeuse-like star, and its antenna temperature is assumed, which is Betelgeuse-like brightness at 1 terahertz with using 10-meter dish with maximum baseline of 6 kilometers is assumed in this case. And the left side shows the amplitude imaging data, aperture synthesis imaging is estimated. By the way, it is just a simple Fourier transform and inverse Fourier transform, and in between just you made input noise, and but I did not apply any UV sampling, but full UV is input, and one UV sampling data, the integration time of 60 seconds is assumed in this case. And in right, the intensity correlation is plotted. But in this case, bandwidth is larger and integration time is longer to get the similar signal to noise ratio. By the way, in this case, the top two shows the phase error of assumed phase error is 50 micro, which do not affect the image. So intensity interferometer requires longer integration time because you have to define the phase with enough accuracy. That is a bad point, but the good point is that when the phase error is larger, the amplitude image degrades rapidly, but intensity correlation is stable against phase fluctuation. That is because this larger single peak, so that the delay jitter do not affect much on intensity correlation. So what is the merit of intensity interferometer? When you use, when the detector sensitivity is much better than what you usually use for heterodyne receiver. So, you know, the space mission, like the far infrared mission, you use cryogenic telescope to get low background conditions. And the detector sensitivity is much better than heterodyne receivers. So the comparison of the quantum noise of heterodyne receiver and background limit of direct detector is made here. when you convert the noise equivalent power of direct detector with background limited direct detector of 10 to the minus 19th watt per root hertz with 100 gigahertz of bandwidth, the noise temperature of the receiver is estimated as 10 millikelvin, which is much, much less than the quantum noise of a heterodyne receiver of 150 Kelvin. So there is a sensitivity merit of more than 4 orders of magnitude. The situation is plotted in this graph. It's a noise equivalent flux density, or NEP, as a function of a frequency. So the quantum limit is plotted in orange. And the background limit, which is by cosmic microwave background and fine field background, interstellar dust emission, it's a large gap between. So the sensitivity of direct detector is very good. By the way, the atmospheric limit is similar to the quantum limit in submillimeter wave, but already the in millimeter wave at 300 gigahertz, the direct atmospheric limit can be lower. So usually a direct detector is used to measure cosmic microwave background in at the millimeter wave frequencies. So the detector technology, when you want to measure the delay time with enough accuracy, the ultimate sensitivity can be obtained by photon counting. The photon counting achieves the background limit sensitivity always. But whether you can achieve such kind of sensitivity or not is a question, and this is the estimate. The required detector noise equivalent power as a function of time resolution, how fast is the detector is. So when the detector responds within 1 nanosecond, this is 10 to the minus 9 second in time resolution, the in terahertz frequency, they all from 0.3 terahertz to 10 terahertz, the photons, all the photons are resolved in time. So the short integration time makes the requirement for NEP, detector NEP, higher or relaxed. So with NEP of 10 to the minus 17th watt per root hertz, which is relatively easy for people working on detectors to get, and you can achieve photon counting, but you need high time resolution. So the technology we are working is a superconducting detector in terahertz frequencies. We are working with niobium SIS photon detector at 650 gigahertz. And this is one of the example of the detector itself is the SIS junction. It's a enlarged view here, and you can see a small junction here and here. And we have already measured the spectral response of this detector, which centered at 660 gigahertz with a bandwidth of 35 gigahertz. We have some a problem with efficiency of this detector still, so we are still working on this. There's another example of a high frequency superconducting detector at 10 micron or 30 terahertz, which is demonstrated by Kawakami et al., which is hot electron bolometer detector. We are now have detector, so we are now going to make an interferometer experiment and set up a cryostat like this with pulse tube cooler. We have not yet have window on it, but we are going to make it soon, and to make a interferometer experiment like the plot like this, so set up like this, which is yet to be made, so it is just drawing. But we have most of the components ready. So now in this year, we are going to set up experiment to show whether terahertz intensity interferometry works or not. So the next step, we are proposing to make the interferometry in Antarctica and high site like Dome Fuji, it is a Japanese site, or Dome A in Chinese site. This is the measurement from Dome A, the Chinese site, where you can observe, you have a good atmospheric window. It is a transmission of atmosphere from 1 to 8 terahertz. It is a measurement, actual measurement. It's the best data actually. Ionized oxygen line from universe can be observed at 1.5 terahertz, and ionized oxygen line at 3.4, which is 88 micron, and 5.8 terahertz, it is 52 micron. And even you can observe ice feature of protoplanetary disk at 43 micron or 7 terahertz in this window. It is interesting. So the future will be the space-borne interferometry. So in this case, two telescopes, possibly on a single launcher. We have cryogenic technology developed for Akari and Spica and Natural Age. It's Hitomi. And VLBI technology we have, and it's Hauka and developed also for Astro G. And superconducting detector technology demonstrated on SMILES on space stations. So we have those technologies. And future will be interesting with combination of large missions like Origin Space Telescope and Millimetron Space Observatory, which are all large cryogenic telescope and with direct detectors. If it is fast enough and you have recorder and clock, then you can make it into intensity interferometry. So you can cover all these gap by space-borne interferometry, possibly with intensity interferometry. And on ground, we'll be able to observe in optical intensity interferometry using Cherenkov telescope array, which is proposed and will be made in at least for experiment. Okay, so it's a summary. I leave it here. Thank you.